Welcome everybody. You might have seen this guy already in the Professor Knoll talk. And I'm the part of the Roboy student team, which is based in the Technical University of Munich. But Roboy itself was initially developed in the Artificial Intelligence Laboratory in Zurich, of the University of Zurich, and it moved to the Technical University. And I'm glad to present the simulation of the tendon-based muscles, because Roboy is the showcase of the use of the software interaction with the user in the complete system, and it's very interesting, and it's only one in its case, and students got interested in developing and working on it. In the May of 2015 we created the Roboy student team, which is now we're split in 6 teams, being electronics, the guys building obviously electronics, required electronics to make him faster and more controllable. Then mechanics guy build new legs for the second generation of the robot. Then we are trying to bring the user interface to the robotic operating system, because it's the standard tool that is used in the industry and it will be convenient. Then we are also bringing the My Robotics elements of Roboy to the robotic operating system for the same reason. Vision guys are integrating Intel's RealSense camera to extend its functionality to recognize users, to recognize their emotions, maybe to learn new movements by demonstration, and so on. And finally, the simulation team, which I am part of, we are working on the Gazebo simulation of Roboy, and yeah, I think it's pretty important. So why do we want to simulate Roboy? Why do we need it? Having a human-like structure, high complexity and high fidelity, it's a compelling area of collaboration for the scientists. But in the same time, this complex structure has new challenges unseen before in the classical robots. And one way to tackle these problems, to cope with them, is to simulate and split it into parts, to investigate each problem in the small part. But simulation is also a challenge, but we'll skip that. So we are bringing Roboy to Gazebo and ROS, because as I've said, it's one of the mostly spread tools in the robotics. So once we have that in ROS and Gazebo, scientists can connect already validated models, control models, to Roboy and test them. So it might be a verification engine for the neuroscience or the test platform for new control strategies and so on. And I will roughly skip through the workflow just on the surface. So first of all, we simulate the skeletal structure, obviously. As Roboy was 3D printed, it's not a problem. If we ignore some tiny details and problems with Gazebo, it was relatively easy because we have all the meshes and we can build the same structure, one-to-one structure of Roboy. Next thing, so we have the skeleton and we also already need muscles. Just for your information, there is a muscle unit, so we have a motor, a spring here, and a tendon, which is inserted to some point on the body. So this tendon coils up on the spindle, contracts, and this corresponds to the contraction of the muscle. Not that difficult, and it seems not difficult, but Gazebo was built to simulate classical robots, only that are built by the kinematic chains of the object, which are connected by joints. And we don't have the tendons, we don't have muscles in Gazebo, and for that we needed to write a Gazebo plugin to simulate that, and then only then we were able to simulate the exact structure, the tendon-driven structure. And in the very end, we added friction models as tendons run all around the body, and in this insertion points and the routing points of the tendons, you obviously have some friction, as it's physics-based models, and also tendons wrap around the bones. That's why we need also to add the wrapping models. And thank you for your attention. I will obviously talk to you in more detail during the poster session. Thank you.